Hello, dear friends, welcome back to Math with Amala. This is the seventh part of grade 11, chapter 1 sets. So far, we have completed up to exercise 1.2. Here we discusses the topic subsets onwards. Let us consider a complete set which is having the elements like R, R, Y, 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 Y. Here let's take the Y sets as the Y and the complete sets as the S. Here Y set is a subset of S because it is included inside the superset S. So we can say that if we have two sets A and B, A subset B, if A belongs to A implies A belongs to B. That is, if A is in A, it should imply that, or it should mean that A is there in B also. A is a subset of B if A is an element of A implies that A is also an element of B. If A is there in the capital A, then that element small a should be there in capital B. This is actually denoted with the A subset of B. With a long C, we will denote it. If it is not so, it is called A is not a subset of B. You will denote it with a striking. If A subset of B and B subset of A, then A is equal to B. That symbol inside is called if and only if. EIFF, which means everything is there in A and B. They are equal. Suppose A subset of A. That means if we take a set A, then A is completely contained in A. There is no doubt also. Phi also will be there in A. That is a null set. That is the empty set or the nothing. It is there already in the A. Phi is a subset of every set. In every set you can't see, but it is there inside. Phi is there inside every set. So you can say Q, the set of rationals, is a subset of real numbers. Q subset of R because R is mother set to all other sets like whole numbers, natural numbers, integers, rationals, irrationals, etc. Okay, second one. A is equal to set of all divisors of 56. B is equal to set of all prime divisors of 56. Here, set of all divisors of 56 is the largest set. So, we can consider it as the superset. And the smaller set is the set of all prime divisors of 56 because we are limiting the condition. So, it will be becoming a smaller set than the larger one. So, you can say simply like B is a subset of A. Third example, A is equal to 1, 3, 5 and B is equal to set of all x such that x is an odd natural which is less than 6. You have to note that 6 is not included there. We have given like x is less than 6. So you will get three numbers 1, 3 and 5. You can simply say A is subset of B, B is subset of A because it contains the same elements. So if and only if condition is arising there, you can say A equal to B. Okay, here we have used the third one, A subset of B, comma B subset of A is implies and implied by A equal to B. Next, A equal to 1, 2, 3, 4 and B is equal to set 1, 2. 1, 2, 3, 4, 5, 6. Okay, we have 6 elements in B and 4 elements in A. It is clearly A is subset of B because 1, 2, 3, 4 is there in B and A not equal to B because B can be considered as the superset which contains 2 more elements than A and this A can be considered like proper subset and A not equal to B. Proper, that properness is coming there which is not including the equal to symbol. Okay, so A is equal to set 1 is a singleton set. This is a proper set, proper subset of A and A equal to 1, 2 is a proper subset. Likewise, we can say that A is equal to 1 is a singleton set. Only single element is there. So, it is called a singleton set. Now, let us consider the example number 9. Okay. 5 comma A is equal to 1 3, B is equal to 159, C equal to 1 3 5 7 9. We have to find the subsetness. Okay, whether phi and how the phi and B is connected, A and B is connected, A and C is connected, B and C is connected. Let's see. Phi is a subset of B. Phi is a subset of every element, every set. But A is not a subset of B because we can see only 1 inside B. No 3 is inside B, so it is not included. But A is there in C. 1 3, the set 1 3 is there in C. Also B 159 is there in C. So C can be considered as the superset and A and B as proper sets, and also phi also as a proper subset. Okay. Example number 10. A is equal to set of all A, E, I, O, U, the vowels in English alphabets, and B is equal to A, B, C, D. So you can simply look at the examples and you can say that only A is there. A is not a subset of B because A is not completely contained in B. But B is a subset of A. Is it true? No, B also is not completely contained inside A. Hence we can say both are not subsets to each other. Example number 11. Let's take A comma B, like it should be like A belongs to B and B subset of C. A is included in B and that B is a subset of C. And the question is that whether A is a subset of C. A is a subset of C. So you can take an example of set A, singleton set A as capital A, and that A is contained inside set B. Okay, so that will be set of set A, B, C. Now we can consider another set C such that C is equal to set A, B, C, D. Now we got B is contained inside C. Now our question is that whether A is a subset of C. It is not true. It is not a subset because set A is actually capital A. And capital A or set A is not there inside C. But A is, so we can say, but A is not a subset of C. Here we can clearly have an explanation like this. Set A includes an element A. Okay. We have to take that, or we have to consider that element only, not the set completely. So inside the C, we must have an A instead of set A. Set A is there is already in the C, but we need only that single element A, not singleton set. We need the single element A inside C. Then only we can say A is a subset of C. But here it is not possible. Hence we can say A is not a subset of C. That is, an element of a set can never be a subset of itself. Okay. Next one, subsets of set of real numbers. Let us consider the real numbers, which includes natural numbers, integers, rationals and irrationals. I have given the irrationals as T, that is set of all x belongs to R and x does not belongs to Q. Actually they are in R but not in Q. Hence they are actually the rationals, which includes root 2, root 3, root 5, etc. Okay. Hence we can give here the subset symbol. N is a subset of set, Z is a subset of Q, Q is a subset of R, then again T is a subset of R, and N is not a subset or not including or not belonging to T. The next part is intervals as subsets of R. We have a mother set R and you can represent it in the number line as a complete interval. Now let's take some parts from the real number line in order to represent the closeness and the openness. Let's take A comma B belongs to R. There are two elements from R where A less than B. A is appearing first when we consider from the left to right, then B. Okay. Then we are moving from A to B. A to B. Now look at the representation. We have an interval. This is an open interval. Open A comma B. It says about all points between A and B where A comma B does not belongs to AB. A and B are not included, but it includes all the points in between A and B. This is called open interval. And if we consider the A and B also inside, including the between points, then it is a closed interval. So set of all points including n points also, it is called a closed interval, where A comma B will be there in the closed interval. Now you can look at the brackets. The difference in the brackets is given there. In the first open interval it is open, and in the next one it is a square bracket. Okay. Now we will have some set builder form for the interval, open intervals, closed intervals, and intervals which are having both open and closed. AB is equal to set of all x such that A comma B belongs to R where A less than x less than B. You have to note this. When we have less than, you will use only open brackets. When you have less than or equal to, you will use closed brackets. Okay. So when we have closed brackets, you have to use A less than or equal to x less than or equal to B. When you have open and closed, you can use like set of all A comma B such that set of all x such that A comma B belongs to R and A less than or equal to x less than B. Then open A, closed B equal to set of all x such that A comma B belongs to R, A less than x less than or equal to B. Okay, these conditions are arising here, and we can simply notate the examples like minus infinity to infinity is coming in the first case, then close to 0 one is in the second case, then close to 0, open infinity. When we take infinity, you will be always having the open bracket. Okay, then minus infinity, comma 1 is the example for the last. Okay, 1 is a closed. What do you mean by B minus A? This is actually the length of that interval. If we take any interval AB, then B minus A, the larger minus smaller is the length of that particular interval. What do you mean by the universal set? Let's consider a set A and a set B which includes A, and another set C or any set U which contains these both A and B. Then the C or the U is called the universal set. You will represent it with the capital big U, which contains all the sets like A, B and C. Thank you all for watching the video. Please stay tuned for part 8, which contains the exercise.